You know, we spend so much of our time looking up at the stars. But what if I told you one of the greatest mysteries in the universe is right here, directly beneath our feet? Today, we're going to take an incredible journey, a journey to the center of the Earth. So let's just ask the big question right off the bat. What is actually down there? I mean, we walk on it every single day, but the ground beneath us hides this whole other world, a world of extreme pressures, unimaginable temperatures, and incredible layers that define our entire planet.
Now, here's the really interesting part. We can't just, drill a hole and take a peek. The deepest hole humans have ever drilled only scratches the surface. We're talking about 12 kilometers down. And when you think about the fact that the Earth's radius is over 6,000 kilometers, well, that's nothing. So we have to become scientific detectives, piecing together all the clues to figure out what's really going on inside.
Okay, so how do we even begin to solve this planetary mystery? Well, all of our knowledge really comes from two main types of clues, things we can physically get our hands on, and these invisible forces that act like a giant X-ray for the entire planet.
Our clues basically fall into two big buckets. First, you've got your direct sources. This is the stuff we can physically touch and analyze. And then there are the indirect sources, which are, in many ways, even more powerful.
Let's start with the direct evidence. That's pretty straightforward, right? We've got surface rocks we can study, and we have volcanoes that bring up magma from deep within. But look at our limits. Our deepest mines only go down about 4 kilometers. The deepest scientific drill I mentioned? Just 12. That is a tiny, tiny fraction of the way to the center. So here's the big takeaway. Direct sources alone just don't cut it, not even close.
This is where our secret weapon comes in: seismic waves. The best way to think of them is like a planetary scale ultrasound. When an earthquake happens, it sends these powerful vibrations zinging through the entire planet. And by studying how those waves speed up, slow down, bend, or bounce, we can actually map out the different layers inside the Earth with incredible detail. It's amazing.
All right, you ready? With our tools in hand, our journey can officially begin. Let's start our descent from the very top layer, the one we all know and love, the crust.
First off, the Earth's thin outer shell, the crust, isn't just one solid piece. Nope. It's actually split into two very different types. You've got the continental crust under our feet, which is super thick but relatively light, kind of like a big piece of foam. But then there's the oceanic crust, which is much thinner but way denser, like a solid slab of rock. And that difference in density, that's what allows the continents to float higher on the layer below. So what's the ground we walk on actually made of? Well, this might just surprise you. Look at that chart. The most abundant element in the Earth's crust is oxygen, followed by silicon. Together, they form what are called silicate minerals, which make up pretty much all of the rock you see around you. Okay, we've passed the crust. What's next? The mantle. And the scale of this thing, it is mind-boggling. Just look at this number. The mantle makes up a staggering 83% of the Earth's total volume. So to put it simply, our planet is basically mostly mantle. And this is not some quiet, calm place. Oh no. You've got to picture this vast region of super hot, dense rock that's slowly churning. It's a process called convection, kind of like a really, really thick soup simmering on a stove. And this slow motion movement is the engine that drives the tectonic plates on the surface, causing earthquakes and building mountains. Now, inside the upper part of the mantle, there's this really weird, really important zone called the asthenosphere. And it's tricky, right? It's not really a solid, but it's not a liquid either. It's this plastic-like gooey layer that the rigid tectonic plates of the crust actually float on top of. And this is also where most of our planet's magma comes from. Okay, we're going deeper. We're leaving the rocky mantle behind us and taking the plunge into the most extreme, most mysterious part of our planet. We're headed for its fiery core. So the core itself, it's really a tale of two very different parts. First, you hit the outer core. Think of a giant swirling ocean of liquid iron and nickel, and all that movement of molten metal is what generates Earth's protective magnetic field. But then you go deeper still, and you find the inner core. It's made of the same stuff, but here's the shocker. It's a solid ball.
So just how hot are we talking here?
Well, the inner core is burning at an estimated 6,000 degrees Celsius. I mean, to put that in perspective, that is as hot as the surface of the sun. So, wait a minute. How on earth can it be solid? And the answer is just one word: pressure. The weight of the entire planet, literally the entire planet, is pushing down on the center. The pressure is so immense that it physically crushes the atoms together, forcing them into a solid state, even though the heat is trying to melt them. Down there, pressure wins the battle against temperature.
Okay, so we've journeyed through all these different layers. Let's kind of zoom out now and see how geologists have actually mapped the precise lines between them. See, these boundaries aren't just fuzzy guesses. They are super sharp transition zones, and we call them seismic discontinuities. These are the exact points where those seismic waves we talked about suddenly change their speed or direction, telling us, hey, you've just crossed from one type of material into another. And scientists have actually named the major ones you'd cross on the way down. Probably the most famous one is the moho, which marks that dramatic shift between the crust and the mantle. Deeper down, you've got the Gutenberg discontinuity, which separates the rocky mantle from the metallic core. And right at the very heart of it all, the Lehman discontinuity marks the boundary between that liquid outer core and the solid inner core. Okay, remember way back when we looked at the crust? We saw it was mostly oxygen and silicon. Well, check this out. When you look at the entire planet, the whole shebang, the picture just completely flips. Earth as a whole is dominated by iron. So where is all of it? Well, most of it sank down to form the core. And this tells the amazing story of how our planet formed, a process where the heaviest materials sank to the center, creating the distinct layers we know today. This whole journey just goes to show you the deep, hidden layers of our planet aren't disconnected from our world up here. They are the engine that shapes our continents and literally protects us. Which brings me to one last critical question for you. That swirling liquid core generates our magnetic shield, protecting us from deadly solar radiation. What do you think would happen to life on Earth if it ever cooled down and stopped spinning?